Welcome to Lesson 2.1, Find Square Roots and Compare Real Numbers. Now, I know you've worked with square roots for years. Your square root is just that symbol that looks like this. Two pieces of the square root that you might not be familiar with the names of is the radical and the radicand. The radical is the sign, like this actual symbol of what we call a square root. The radicand is the part that goes onto the inside. So say we have the square root of 25. Our radical is the sign that goes around the 25. The radicand is the 25 itself. As you will go into higher level math classes, you will sometimes hear other math teachers refer to square roots as just radical, or rad for short. So if they said like 3 rad 2, that would be 3 rad 2. And that would be one way that they might just do more of a verbal shorthand as they are talking about various things involving square roots. So let's do some practice problems from the book. So you might be asked to evaluate. And remember, when you multiply two numbers together, say 6 and 6 to get 36, you could multiply both positive 6 and positive 6 to get positive 36, or you can multiply negative 6 and negative 6 to get positive 36. So your book notates this when it's looking for an answer to a square root by putting this plus or minus sign in front. And all that says is we want both the positive and the negative answer. So since both positive and negative 6 squared will get us to 36, our answer would then be positive 6 or negative 6. So if you put plus or minus 6, that gives both answers in a nice condensed shorthand. For the square root of 49, it says nothing about positive or negative in front. So your book, with its notation, it just assumes that you will interpret this as looking for the positive solution to the square root of 49, which in this case is 7. Or for the last problem that we have here, the negative square root of 4, the negative is there to let you know that we're looking for the negative solution. So our answer in this case would be negative 2. Now we are going to move into something called the perfect square, just as a brief thing to talk about. A perfect square is when you have some term that is squared. So you could have a 2 squared, which would give you a 4. You could have an x squared, which would give you an x squared. 4x squared as a term is still a perfect square, because it's the same. If we take the square root of that, that would come out to be a 2x. So 2x squared would get us to that 4x squared, and therefore that is a perfect square. Oh, whoops, this got condensed a little bit closer than I meant it to. So let me shift that down. There we go. So the area of a square is 945 inches squared. What's the side length to the nearest inch? Well, for that, all you end up having to do is you just take 945, whoops, forgot my 4, 945, and take the square root of that. And actually, I'll show you that on your calculator, because if you're not familiar with your graphing calculator yet, you might not know how to do the square root. So popping over to our graphing calculator quick, what you'd have to do first is press second, and then this x squared button, because the second will activate your blue options above the buttons. And if you look at your x squared, you have a little square root sign right here. So we want the square root, and then it was 945. So now you would type in 945. On this older operating system, and we'll put it inside of parentheses, so you can close that off if you would like. On the newer operating system, it will actually let you type it in underneath the bar of the radical. Either way works just fine. You'll come out with 30.7, and it wanted it to the nearest inch, so our side length would be about 31 inches. So then we can come back here and say that that comes out to be about 31 inches. And actually a nicer way to say about in math terms or math notation is you use these squiggly lines to say the square root of 945 is about 31. You're not saying that they are perfectly equal, but you're saying it's about that. Now, some things that we're going to have to talk about is categorizing numbers. So we have a number of different categories, and all the math we're going to do here in Algebra 1, that all the numbers we work with will be real numbers. So anything that you can imagine, Right now, that's currently a real number. So we'll actually work from the smallest circle all the way back out to the biggest. So our natural numbers are the numbers that come up in nature as we're counting things. So you can have 2 trees or 8 cars, but natural numbers, they're all countable, nice numbers, no decimal places, no fractions, no none of that. But there's no zero. So what this is just dating back way back to original understandings of mathematics. People didn't see a reason to have zero, and so they just didn't develop that as a concept. Well, then at some point, someone does come along with the idea of, oh, we should have zero now be an option, because zero is actually really helpful, especially if we're talking in terms of money. Because if you spend everything you have, now how much do you have? Zero. You have $0 left, or 0 coins left, or whatever term of money you're using. So whole numbers are all of your natural numbers. So, and then we'll also include 0. Your integers, this is now when we start introducing our negative numbers. So this is when we can have like -2, -5, or you could have 3, 17, 51, something like that. And so your integers are just your positive and negative whole numbers. It still also includes 0. So your natural numbers are all whole numbers. Your whole numbers are all integers. Your integers are all rational numbers. But what makes the rational numbers different? These are any number that can be written as a fraction. So you can now have partial wholes. So you can have 2/3, or 3/2, or 17/51. Whatever you want, you're able to do it as a fraction. And as fractions, you can still write whole numbers as a fraction. That would just be like 2 seconds or 5/1. So this is where the rational numbers start to be different. Irrational numbers, on the other hand, since those circles do not overlap, are numbers that can't be written as fractions. They are numbers that, if they are a decimal, they keep on going for forever without ever repeating. Something that you know that's like that would be pi. Pi is an irrational number. Uh, you will also see square roots in here if the square root can't be simplified. So like the square root of 2, the square root of 7. Those would all be irrational numbers. But both irrational numbers and rational numbers combined make up the whole set of real numbers. All of these numbers exist, and so we call them real numbers. When you get to Algebra 2, we'll start exploring non-real numbers, which are also called imaginary numbers, which is a terrible misnomer, but it's a name that's stuck, and so that's what we end up teaching. But that's not what we have to worry about now in Algebra 1, so we'll just move on. So what we have to do now is we have to classify the following numbers. The square root of 24. Does that simplify nicely? Square root of 25 would be 5, but this isn't 25, it's 24. So no, it doesn't. Since it doesn't simplify nicely, that means it's going to be an irrational number, and it's also going to be real, because all of these will all be real numbers. Square root of 100, well, again, with the notation of your book, this is looking for the positive square root of 100, which is 10. And 10 fits everything that we just talked about that's not irrational. So we start out from natural, then we can go to whole, because it's natural means it's positive whole number, good. Whole means it's a positive whole number, good. Then we go to integers. Then after integers, then we go to rational. And then after that, we go to real. So that's all the different classifications that 10 could have. The last one here, -81, or negative square root of 81, comes out to an answer of -9. And that isn't natural because it's a negative number. It isn't a whole number because it's a negative number. So this is going to be an integer, a rational number, and a real number. And I'm just going to abbreviate those because you know what they stand for. Something else you might be asked to do in this section is order numbers from least to greatest. What I would suggest doing here is figure out what they are as evaluated numbers first, rearrange it like that, and then come back to put it off of what they were originally written as. So like the square root of 9, we can call that 3. The square root of 13, I'm just going to type that into the calculator real quick because I don't know what that comes out to. And the square root of 13 is 3.6. The negative square root of 5, well, that's going to come out, according to the calculator, it's going to be a negative 2.24. And then we also have that negative 2.5. And 4/3 is going to be 1.3 repeating. Oh, that is something I forgot to mention. With your rational numbers, you can also have decimals that repeat. So even if it's like 1.123 and it repeats that 123, that is still a rational number. You can actually write that as a fraction. Or you could have a 1/3, which would be 0.3 repeating. That would also be a rational number. So now coming back to our numbers here, we now just have to order these from least to greatest. So least would mean the largest negative value. So that would be our negative 2.5. Then be our negative 2.24. Then our 1.3 repeating, our 3, and then our 3.6. We're not quite done yet because we do have to rewrite this off of what the numbers originally were. So that negative 2.24 would be the negative square root of 5. Your 1/3, or sorry, 1.3 repeating is going to be 4/3. And then your 3.6 is going to be the square root of 13. And now we have our numbers in their final order. So we've got our answer. The last thing I believe, last thing on this section is something that's going to be hit a lot harder in geometry, but we do have to introduce it here. So a conditional statement is something like you would see, actually you hear conditional statements all the time. What it is it's given a condition and then a response to the condition. If you haven't cleaned your room and your parent goes like, if you don't clean your room by the time I get up there, you're going to be grounded. That's a conditional statement. If you don't do this, then this is going to happen. There's a condition placed on what needs to happen, or else there will be a consequence. That can happen actually in math as well. So we might get the statement, no fractions are irrational numbers. Well, it takes a little bit of thinking to figure out how to write this as an if-then statement, but you have to start out with what is the premise? What are we talking about? Well, we're talking about fractions. So if it is a fraction, no fractions are irrational. It's saying that fractions can't be irrational. So then it's saying that then not irrational. And that would be rewriting this conditional statement in if-then form. Well, if it can be written as a fraction, we know that's a rational number, and therefore not irrational. So this is true. And it actually wants us to tell if it's true or not. So we can say that's true. The next one says all real numbers are rational numbers. So just like the last one, if it is a real number, well, all real numbers are rational. So if it's a real number, then it's a rational number, would be the then part. The problem with this is that irrational numbers are also real. So this one is actually false. Now, the last part of what the question asks, it says, if it's false, give a counterexample. A counterexample is just one time when it's false. If a statement is true, it's going to be true every time. But if it's false, you only need one example for it to be false. So an example of a real number that is irrational, you could do pi. Pi is a real number that is irrational. You could say the square root of 2. You could say the square root of 51, or of 3, or of 17. Or when we get into Algebra 2, you'll also learn of another number called e. All of these would be irrational numbers that are also real. So you could write any of these down as a counterexample. So that's it for this lesson. So if you have any questions, make sure you let me know, and otherwise, good luck.